video is going to be combining the 1.5 and 1.6 sections of our book about transformations of parent functions. This video is featuring my messy room and all the papers I have to correct. The objectives are going to be becoming familiar with the 6 main parent functions. There are 6 functions that you have to recognize the shape of, and 6 functions also in the other way that you have to look at the equation and know what the shape of the function looks like. So that's one major thing. You need to know those shapes. And then also we're going to be looking at 2 transformations for now, shifts and flips. These are the first shapes that we're going to be studying, the first parent functions. They're the 3 of the 6. And we're going to start out with kind of a basic one that hopefully we all recognize, a quadratic. If there's nothing being added, nothing being multiplied, it's just an input value to the second power. What we're talking about is the parent function quadratic. No shifts, no nothing, no transformations, just a stripped down basic shape. So in the past what we could always do is an xy table. I am going to use f of x because we need to get in the habit of, this is just another notation for y, or output value. We could plug in input values, get a good span here, and then input those into our function, which would square all these values, and we would get these. So as you would graph these, you would get points, and if you connected those dots, you would get a shape. Oops. So this one's a big one. This one is what we call our vertex. It's either the maximum of our parabola or the minimum of our parabola, in this case the minimum. And so if you could then, instead of having to do an xy table all the time, if you just know the shape and you can identify that beyond this very key point of the vertex, which rests right on the origin when there are no transformations, beyond knowing that point, you can just go back 1, up 1, forward 1, up 1, and then know that you're going to do the U shape through it. You're good to go. That way you don't have to do this every single time. And it's really going to help you if you know those key points as you shift these in the future. Here is the cubic. We have a very mathematical term for the shape of this one. It's a squiggly. The pivot point, big point about this one. It's just as big as the vertex over here. This one's our pivot point for the cubic. That rests also on the origin, and it's kind of like a half parabola. Again, you would go over 1, up 1, back 1, down 1. So those are key points, and then you kind of draw half parabolas, one going up, and then at that pivot point, one going down. It's a little bit steeper than a parabola because, of course, it's a cubic. So if you went over 2, 2 cubed would be up 8. So from that central pivot point, over 2, up 8, or over 1, up 1, draw your parabola, half parabola, then pivot it to make a squiggly. Okay. And we also have the square root, key points about that. This one starts at the origin as well. We're starting to see the origin is a very important piece. So the origin is our start. Again, over 1, up 1. And then if you know that it's an arch, you can kind of guide that arch through those key points that you have. Note that this is only taking up part of our coordinate plane. Part of our coordinate plane. Okay, so, sorry, where was it? Oh yeah, this is only on half of our coordinate grid. So what we do know is because our domain for this one has to be positive, this parent function has a domain from 0 to infinity, and we do include 0 in the input values, and so that's why we only get a graph that's on this side of our coordinate grid. The next graphs, these ones are a little bit newer. I'm going to go into this one, more into that one in a second. The reciprocal one is an interesting one. It's also called, the inverse function. And I guess the shape for this one, it's really guided by what we know as asymptotes. So these asymptotes sit right on the y-axis and the x-axis. So you basically can just say, well, the coordinate grid kind of guides these as well. So once again, from that origin point, we would go over 1, up 1, okay, back 1, down 1, and then from those, we kind of sketch out or sprout out this curved shape, and we get ever closer to our x-axis, but we never cross it. We get ever closer to our y-axis, and we never cross it. And same thing with this little arch down here. So one of the reasons, don't take my word for it, if you needed to, you could do your xy table. Let's plug in a very small x. Let's plug in 1/10. Okay? So if we inputted that in, it would be 1 over 1/10. And then what we would say is, well, we have a number divided by a fraction. We know we can change division into multiplication, but then you have to flip the denominator, or the divisor, into its reciprocal. So we get 1 times 10. So actually, as these get smaller, the y's get larger, and that's why we also call it the inverse. So you can see here, as we get smaller with the x values, they're going to be shooting up and getting up towards infinity. Okay, so that's this one. Again, we have over 1, up 1 from that origin, and back 1, down 1, and then you spread out. Absolute value, I think hopefully this one's pretty recognizable. It's the V shape. The absolute value, what we've always learned it to be is whatever value you put in those absolute value bars will change up positive, and it's because it's defining a distance, and distances are always positive. So that's why we get those positive values. But you plug in -2, you're going to get positive 2. You plug in -4, you're going to get positive 4. And so you can see why we have these lines, one with the negative slope, one with the positive slope. Makes a V. Okay, so the very last one, this one's new to us. The notation that I have isn't the best. I couldn't find the symbol for it. But what it is a square bracket with kind of a double bar line inside there. The shape of this is the staircase, all right? It's kind of strange, but what we do is we start at the origin, whoops, and then there's a little line that goes all the way up until our whole number 1, and then once we get to that, we do an open circle, jump up, close circle on the next number. So we don't include 1 in this little line. We have the y value of 1 up there. And then another line, open circle once you get to the integer or a whole number, and then you jump up, and so on and so forth, okay? And then same thing, you would just have to do the stair steps back. The greatest integer value function is defined right here. It's the greatest integer less than or equal to the input, and I'm going to write that, input. Okay. Alright, so it's the greatest integer, so this is the same thing as a whole number, value, less than, or equal to the input. So with that in mind, let's do it a couple examples. One thing that I like to use is the number line to drive this understanding. Let's look at the value 2.1. Right, so I'm just going to kind of plot some points on a number line. We have 1, 2, 3, 4. Alright, 2.3 would be located right here, right? So what we're going to be trying to find is the greatest whole number. So a whole number that's less than or equal to that input. So we could have done 2, we could have done 1, but we want the greatest possible one, so we're going to just go to 2. It's going to be the whole number directly to the left of whatever our input value is. So this one right here would just be 2. Alright? I'm going to just do another example here. What if we had 2.8? Some people would be prone to say, hey, well, it's 2.8, it's closer to 3. But again, we want something that's less than or equal to it, so we're going to go down again to 2, because that is the greatest integer value that's less than or equal to 2.8. This one's a little strange, 0, -1, -2, -3. Alright, -2.3 sits right here. Right, and we want the greatest integer value. So it's either going to be -3 or -2, but then it has to be less than or equal to, so we're going to go down to -3. This is -3. 10 is just 10, because it can be equal to that input. So I'm just going to go back up here real quick, and then just kind of show you what that looks like then. So when we were doing like the 2.3, then the output, if we inputted 2.3, the output, or the y value, would have been 2. So that's why we were on that flat line. When we did 2.8, it's also on that flat line. When we got to 3, though, we would have to jump up, because then the output would be 3. Okay, and same thing for all of those values. So that is the greatest integer value. From your homework, here is an example. So let's go ahead. We have the greatest integer value function, or bars, around this whole thing, or this expression. So again, this is just notating that we want to input -2 for our x, or our independent variable that's been identified. So we're going to plug in -2 for our x, and it's just saying add 3 to a number, and this is the number. So this is what we get, 1. So the greatest integer value, or the greatest whole number less than or equal to 1, is 1. Okay, 1/2, let's look at that one. So if we were to take 1/2, plug that in, add 3 to it, we would get 3.5, or 3.5. This is again where if you were on that number line, you would be at between 3 and 4 right there, and we want the greatest whole number that's less than or equal to it, so this is equal to 3. H of 1/2, when you plug that in, is 3. 4.2. So this thing is equal to, not this thing, but this thing, is 4.2 plus 3. Okay, and then we get 7.2. So this thing is equal to 7. And then finally, -21.6 plus, I ran out of room, 3. So double bar line, that's there. What we would get here is -18.6. And this is where you have to be a little careful, because we have -18, -19, -8.6. It's right about there. Okay, and we want a value less than or equal to -18, so we would go down to -19, because -18 would be larger than it. So -19 is what we want. Alright, so we've gone over these. Know the shapes. If I ask in class, oh, what does a cubic look like? Be able to tell me, oh, squiggly, or be able to be like, oh, it's a squiggly with some sort of motion. Know what they look like. Okay, so we're gonna, for now, ignore these two. Okay, we don't need this just yet. For now, we're gonna look at shifts, which are going to be addition and subtraction. So addition and subtraction is what we're going to be looking out for, and subtraction of some sort of numbers. Okay, these are going to indicate shifts. So if you ever have a whole function and you have plus minus a and it's not attached to the x, so it's not with the x, what that is it's a shift up or down that many units, and it's exactly what you would think. Okay, so we'll go over this in a second. This one I have a typo. It's either shifted left a unit or right a unit. Alright, this is with the x. Emphasis on the with. Can't really emphasize it anymore. It needs to be either squared with the x, or it has to be, it's this addition that's being cubed with the x, or it's under the radical with the x. It has to be with the x, and then we know it's horizontal. Everything to do with x is horizontal because it has legs. Eggs can go eggs. Oh my gosh, x has legs. It can go back and forth. It's horizontal. So opposite of what you would think, though. Keep that in mind. I'll go over that in a little bit. So let's look at an example. So this right here is where it's not attached to the x. It's this plus 2 is not being squared with the x. It's just out here on its own. So this is vertical. This right here is being squared with the x, so this is going to be horizontal. Alright, it's a horizontal shift. So these are both shifts. It's addition or subtraction. So this one right here is going to do exactly what we would think. We're going to go up 2. So this origin, think of like this origin that's been shifted up here. Okay, so if you wanted to, you could draw a pseudo or a fake x-axis, because now we're going to pretend that we're up here. Okay, and we're going to do the same parent shape that we're used to. You know the vertex normally sits on that origin, okay, and then you would go over 1, up 1, over 2, up 4, back 1, up 1, back 2, up 4. Done. Okay, so there's that. And that's why it's really nice to know those shapes, because as long as you know the shape, you can just go wherever the shift is and do exactly that shape, but with that shift. Okay, horizontal. So let me see, I might have a different color marker. Ballpoint pen. Alright, so we're going to do ballpoint pen. So this one is horizontal. I'm going to graph this one in ballpoint pen. So this is the opposite of what we would think. Okay, so I'm going to go ahead and go back 2. And then this is a new origin right there. So here's my new y, here's my new x-axis. Okay, so here would be where my vertex would sit on that origin. We would go over 1, up 1, back 1, up 1, back 2, up 4, back 2, up 4. Alright, so this would be, oopsies, sorry, that was bad. And the new parabola, where it would sit. Some people wonder why that is. My only possible explanation that I can give you is this. If you were to say, alright, the typical parent function would have been sitting right here, right? Why does the x do the opposite of what we would think it would do? Why does it go backwards instead of going forwards? Alright, so here's my typical parent function. And I'm going to graph that as g of x equals, and then x squared. So we have those values, -2, -1, 0, 1, 2. We would have 4, 1, 0, 1, 4, if we plugged it into the parent function. So now here's the deal. X has something being added to it. And if we wanted to maintain those same y values, so if we still wanted to get a 1, what's going to happen is these x values are going to have to compensate. Okay, so let's say that I still wanted to get this 4. We wouldn't plug in -2 anymore, because if you plugged in -2, you're going to be adding 2, right? And that's going to change the fact that you're going to get 4. So instead, what if we wanted to undo this addition of 2? Well, this value I would subtract 2 from, right? Because that way, if I subtracted 2 from this -2, I'd get -4. And when I added 2, I would get -2 again, and then it would just be -2 squared. Okay, so that probably was really confusing. But let's just say if you plug in -4 here, that way we would have -4 plus 2, because that x knows that something's being added to it, so it compensates for it. Instead of just being -2, it brought itself down to -4, so that when we added 2, we're going to get the typical -2 squared to get our 4. Okay, so this point right here, this typical -2 to go up 4, backed itself up 2 values. Okay, that's my only possible explanation for why it's the opposite of what you would think. So at this point we've gone over the parent functions. We've also gone over the transformation that includes addition and subtraction, where there would be shifts left or right, up or down. So now what we're going to do is the transformation of flips. Flips are going to be where you're either going to flip the entire shape over vertically, or you're going to take that shape and flip it horizontally. So if that negative sign is not attached to the x again, what we're then going to assume that it's attached to is the y. So this is going to be a vertical, so upside down flip, reflected about the x-axis. Right? And then if it's attached to the x, like down here, it's going to be the mirror of f of x, or reflected about the y-axis. This is going to be a side-to-side flip, if you want to do that side-to-side, or horizontal flip. So just like we had one versus the other, we're going to do that again. So this is a little bit hard to see, but this is not technically directly attached to the x. So do note that, because if you were to do the order of operations, you would square that x first, and then you would negate it, right? So this right here is actually not attached to the x, it's vertical. It's not being squared with the x, therefore it's not with the x, so it's with the y, it's vertical. This one right here is attached directly to the x, this one would be horizontal. Okay, so at first I'm going to start out by graphing our normal parent function. So typically it would be on the origin, over 1 up 1, over 2 up 4. So again, knowing our parent function shape is so helpful. Oh, sorry. Okay, so there that is. Alright, then what we're going to do is, if you ever wanted to, you could also plug these in, x, y, but you'll see why that's not very helpful. So this vertical, we'll see what it does here. If you were to plug in 1, let's do our -2, -1, 0, 1, 2 again. If you were to plug in -2, it would be -2, right? And then negated, because we plugged in 2 for the x, so we have a negative to the second. Right, so this would actually be 4, because -2 to the second is 4, but then it was negated, so it's -4. This point right down, instead of being back 2 up 4, would be back 2 down 4. So we'd be sitting right about there. Alright, same thing for all those values. If you try to plug them in, what just happened here was a vertical flip. It was not attached to the x, okay, and so therefore it was a y kind of transformation. This one right here, go ahead and try to plug it into the x and y value, but if you just know that this is a horizontal flip, then we could go ahead and just say, alright, all these values are going to flip around. And what you'll notice, horizontal is a little bit weird for the quadratic, because if you flip this around, it's going to be the exact same values. Give it a try with the xy chart, but otherwise, I mean, it's exactly the same. Okay. Alright, this is one thing to note. We're going to perform this type of transformation. What's going on is we're adding something to the x, we're adding something not to the x, and then we're negating all of these. So we're going to do this transformation. So do your shifts first, always, alright, and then apply the other transformation from the new origin. So you're going to pretend that you have a new origin, and you're going to then do any other flips, or when we get to them, stretches and shrinks at that point. I'll show you what I mean. Alright, so let's look at what this would look like if we had the quadratic. We're saying we're negating the whole function, we're adding 1, and we're going to be adding 3 in the vertical. So this is what this would look like. F of x is equal to, and then negative, in parentheses, x plus 1, because this is outside, so we're just saying it's not directly attached to the x plus 1 squared, because that's directly attached to the x, and then plus 3. Alright, so we're going to look at what this all entails. So I'm going to go ahead and do my shifts first. I know that this 1 is going to bring us back, and then I'm going to go up 3. Okay, there's my new origin. So then the other thing is I've gotten that. I know the shape is going to be a parabola, but then I have to negate it. So I'm going to go from this point, because this is my new origin, back 1, down 1, because typically for our shape we would go back 1, up 1, back 2, up 4, right? But because it's flipped, we're going to go back 1, down 1, back 2, down 1, 2, 3, 4, okay? And there you can see the shape. And I'm not even going to try to connect the dots because I've been doing a really bad job. But there you can see these transformations complete. Let's try it with the cubic. So again, we want to have a horizontal shift, a vertical shift, and then a vertical flip or negation. So this function would look something like this. Okay, so again, we're going to get a new origin, which is back 1, up 3, opposite of what we would think for that horizontal. There's my new origin. Okay, and then instead of going over 1, up 1, we're going to go over 1, down 1 because of this vertical flip. Okay, back 1, up 1, and then we're going to draw our, I'll do this, over 2, down 1, 2, 3, 4, 5, 6, 7, 8. So it's something there is my pivot, and then it would be doop, doop. Sorry, so there we have it, something like that. Alright, same thing, f of x equals, alright, so again we want that plus 1 with the x underneath the radical, because it's with that x in this parent function, and then we're going to add our 3 outside, okay, and so this one would be back 1, up 3, and then instead of going over 1, up 1, we're going to go over 1, down 1, and we're going to do our arc in the opposite direction. So if you knew that we would go over 1, 2, 3, 4, and then up 1, 2 for our typical parent function, you would know now to go down 2 instead. So there is a guiding pathway for my arc. Okay, there it is. Alright, and then this one is a little bit more complex, so I'm going to go back. Okay, so same things apply. So here, what this would look like is I would negate everything, right? And then I have x plus 1 down at the bottom, okay, and then I would add 3. So that's what this thing would look like. So I'm going to go back 1, up 1, 2, oh, that was 2, and then there's my 3. So this technically is where my new origin would be, my x and y axes with those asymptotes that lie right on that. So from that origin, I'm going to go over 1, up 1, oh, pardon me, sorry. So this is negated, so I'm going to go over 1, down 1, okay, and then I'm going to sprout out and approach those asymptotes, but never cross them. Back 1, up 1, and then sprout out and never cross them. And you can see how that was a vertical flip. I took this and I like yanked it down, so this came down here, this arc went up there, but we have those new locations for them because of the shifts. And this one, I'm going to draw this just really fast. Okay, not the best. This one's going to be probably the hardest for you to get used to, but we're going to bring this origin back 1, up 3, just like we've been used to, and then we're just going to draw our stair steps just like normal. So we need an integer lengthwise, and I'm going to close this. Instead of going up to the next integer and drawing my thing, I'm going to draw down because it's the flip. Okay, down because it's the flip. Oops, sorry. These are my solids. This is an open. I'm sorry. Okay, and then so on and so forth. And then this would be likewise in that direction. Alright? So just be able to identify these two from a graph. So if you saw this graph, you would be able to say, alright, this was the normal V shape. We would go over 1, over 1, oh wait, over 1, up 1, over 1, up 1. Okay, so you could acknowledge that that was the normal V shape, but it's been shifted back 2, down 1. So then how are we going to write that? We know we're going to play around with this function right here, the absolute value, because when you think absolute value, you think the V shape. But then in order to get back 1, we would want to attach something directly added onto the x or subtracted. And because it's backwards and it's the opposite of what we think, it's going to be plus 2. Okay, and then in order to get it down 1, we're going to go minus 1. There, I'll call it g of x because it's just been transformed, is that particular function. And if you graph this on your calculator, you would get something that looked like that. There are your homework problems. Good luck.